Jai to all. I am Samender Singh, Assistant Professor in CSC Department in AKGEC Ghaziabad. So today I will discuss about syntax analyzer, parser, context-free grammar, parse tree. These are some fundamental topics. We have some basic idea behind these 3 or 4 topics, as we will discuss these topics earlier. Now I will focus on basically these 2 topics, that is left recursion, left factoring. These are very important topics regarding our compiler design. So we will start with syntax analyzer. It is the second phase of the compiler design. As we know, first phase takes input strings token and convert these input string symbols into tokens, and these tokens will be inputted to the next steps, that is syntax analysis step, and this complete process is known to be syntax analysis. So what is syntax analyzer? It creates the syntactic structure of the given source program, and this is syntactic structure is mostly a parse tree. As we already know, syntactic structure is a parse tree, and it is done on a small class, or we can say very common class of a grammar, that is context-free grammar. It is also known as parser. This is the common name of this syntax analyzer. And syntax of a programming is described by the context-free grammar. We will use BNF notations in the description of CFG. As we know, there are 2 types of normal forms. First is Backus norm form that are used by parsers, and second is GNF that will not beneficial for parser. And next, syntax analyzer checks whether a given source program satisfies rules implied by the context-free grammar or not. If it is satisfied, the parser creates the parse tree of that program. Otherwise, it will show the error message. As we already know, there are 2 functionality of each step, whether it will satisfy. If it is satisfied, then it will produce the required output of that. Otherwise, it will print the error message. And then context-free grammar, it gives a precise syntactic specification of the programming language. It is very common grammar. The design of the grammar is an initial phase of the design of a compiler. A grammar can be directly converted into a parser or by some other tools. Now these tools are very common to each other. Now discuss about parser. Parser works on a stream of tokens that are the output of first phase, and smallest item is a token. This is the block diagram of first 2 phases of the compiler. In the first phase, that is lexical analyzer, it will take the source program and then convert these program into tokens, and these tokens will be inputted to parser, and after getting first token process on this token, it will send request to get another next token for their processing, and as an output it will generate a parse tree. So input is token and output is parse tree. This is all about parser. We categorize the parsers into 2 types. First is top-down parser and second is bottom-up parsers. As the name suggests, their definition. In the top-down parser, we are starting with the start symbol up to leaves. Leaves are what? These are the string symbol. Suppose we have string id plus asterisk id. This is our string. So these symbols, 5 symbols we have. First is id, then plus, then id, then string, asterisk, then id. These are all known to be leaves. So we are starting with start symbol. Suppose this is non-terminal, and as a target we are our leaves, that is these terminal symbols. So these is known as top-down parser, starting with start symbol up to leaves. Okay. And now second category of parser is bottom-up parser. It is just the reverse process of previous one. So it will start with leaves, these leaves, and reach up to start symbol. So these are 2 category of parser. Now, both top-down and bottom-up parser scan the input from left to right. That means first this, then this, then this. So left to right we have these parsers are going to scan. Then efficient top-down and bottom-up parsers can be implemented only for subclasses of CFZ. I told you earlier that grammar used by parser is context-free grammar. Now, LL for top-down parser, LR for bottom-up parsers. You can see there are two alphabet. In first case, LL. Here L means left to right, and second, left to right is common in both, and second is L and R. LR means these are the type of derivation. What is derivation here? Let's discuss it. Let's discuss this derivation after few slides. Now, inherently recursive structure of a programming language as defined by context-free grammar means these majorly programming languages are defined by the context-free grammar. So context-free grammar is a 4 tuple, is defined by 4 tuple. First tuple is finite set of terminals. Then second tuple is finite set of non-terminals. And third is production rule. And fifth is start symbol. So we can say terminal, non-terminal, production rule, and start symbol. These are the 4 tuples of a context-free grammar. So terminal you know very well, non-terminal, and start symbol. These 3 are common to each grammar. Now for context-free grammar, P must be this type, that is A gives alpha. Means every production of the grammar must satisfy this one. Left side of the production rule must be a single variable, or we can say single non-terminal. And right side will be alpha. That is alpha is what? Non-terminal and terminal union of this one, and take the star closure of this one. That means any possible combination of non-terminal, terminal, and using these two. And fourth is the start symbol, which is also a non-terminal. So this is the example of context-free grammar, in which we have first production, then second production, third, fourth, fifth, sixth, seventh. 7 production rules. You can see in each production, left side contain a single non-terminal and right side contain. In this we have terminal and non-terminal, means combination of terminal as well as non-terminal. In all the productions it will follow this. So this is a very common context-free grammar. Now derivation. What is derivation? I told you string start symbol. Start symbol is a non-terminal. So, procedure of start symbol to given string. We can say number of steps through which we are starting start symbol to the given string. This is known to be derivation. Suppose this one. We are starting with start symbol E. In the previous example, we have E as the start symbol. So suppose we have string this one. So we can check by means of number of steps. So we can generate this string starting with E. Then we can see there are number of production rule. We are taken this production rule, that is E plus E. After a number of replacement, here two non-terminal that can be replaced. So we are using ID. Why we are using this production rule? As the first symbol is ID. So we must change this non-terminal into ID. So we are checking this production. First symbol is E, capital E. This is differ from this one. Leave it. In all these, this production rule contain first symbol is minus. This is differed from our given string. So leave it. In the next, first symbol is what? A starting parenthesis. Leave this. And finally, in the last, that is appropriate to given string, we take this one. So we make first replacement, that is E is changed to ID. So starting with first, we are using first production rule. After that, we are using E gives ID. So this is production rule number 7. So two steps. In first step, we are taken first production rule. In second, first symbol is converted into ID. In the same manner, we are matched with this one. First symbol is matched, then second symbol is matched. Now this is not matching, so we need an appropriate production through which we can replace this E into our required next symbol, that is ID. So in the next replacement, we also changes E gives to ID. So these are the complete scenario where we convert starting symbol E into given string. So we utilize 3 steps in which we are taken starting symbol and finally we got the required given string. So this complete process in which we are taken 3 steps is known to be derivation. This is what. Here you can see it. This derive from this one, as this is a first production rule. In the same manner, we are converting first production rule, then this is converting to ID. So two symbols are matched, then this is also replaced by ID. So this complete process is known to be derivation. We can see a sequence of replacement of non-terminal symbol is called derivation, as we did it in the previous example. That is ID plus ID is getting derived from starting symbol E. In general, a derivation step is this one, where alpha and beta. What is alpha and beta here? I told you that alpha and beta are the all possible combination by means of non-terminal and terminal. So alpha, then we have non-terminal, then we have beta. This is converting to alpha, gamma, beta. But when we are converting, if there is a production where this replacement can be achieved. That is, this production will be there in the production rule set. This is what. So, in our grammar, where alpha and beta are terminal and non-terminal symbols, possible combination. So, these we can say alpha 1 first step, then alpha 2 second step, and finally we are getting our string after number of steps. So, we can drive our required string in one step, in 0 or more step, or we can say in 1 or more steps. Now, CFG, that is context free grammar. What is this? Suppose LG means we have a language of grammar G, CFG, which is a set of sentences. Set of sentences means it is a possible string that can be legally derived. A sentence of LE is a string of terminal symbols of Z. If S is the start symbol of the grammar, then this is start symbol to omega. What is omega here? It is a string. Where omega is a string of the. If G is a context-free grammar, LG is a context-free language. Two grammar are equivalent if they produce the same languages. We can say this one is starting symbol to alpha. If alpha contains non-terminal, it is called as a sentential form of Z. If alpha doesn't contain non-terminal, means it will contain only terminal symbol, then it is called sentence or string of the G, grammar Z. Derivation example, we have number of examples. Suppose we have, this is our required string. So starting with the start symbol, then first is what? Minus. So we are utilizing a production that will tell E gives to minus E. So first symbol match with given string minus. Then we can see here second symbol is what? Starting parenthesis. So we need to convert E to this starting brace, then E, then closing brace. This is our second production, or we can say second replacement. In the same manner, next is ID. So ID, after ID we have plus, so we are utilizing this, or we can convert this E is into E plus E. After that E, we are converting E into ID. So we are matching three symbols. First is minus, then starting symbol, then ID. After that for ID. So we are match four symbols. After that we have non-terminal. So finally we convert this non-terminal into ID. So you can see that this is our required ID. So this is our derivation. This is, we are achieve this string by means of another path. So at each derivation step, we can choose any of the non-terminal in the sentential form of the G for the replacement. Here you can see we have two non-terminal. So we have possibility to change either this or this. So we can say in the sentential form, we can choose any of the non-terminal. Here too, so any non-terminal can be chosen for replacement. If we always choose the leftmost non-terminal in the derivation, here only one non-terminal means no. It is leftmost, it is rightmost. The same here we have two non-terminal. If we are choosing this left non-terminal for replacement, then it is known to be leftmost derivation. If we are choosing right non-terminal for replacement, then it is known to be rightmost derivation. So in each step of the derivation, if we are going to replace leftmost non-terminal, then it is known to be leftmost derivation. And in the same manner, if we are choosing rightmost non-terminal for replacement, then this approach is totally reverse from first one, that is rightmost derivation. I hope you can understand this topic. Now these are the example of leftmost derivation and rightmost derivation. We can see leftmost derivation. Suppose we are converting this to D. Since we have only one non-terminal, so it will not reflecting the real scenario. Now E is converted to E plus E. Now you can see this leftmost, this is left symbol. Yeah, we can, two non-terminal is there. First one is this and the second one is this. So this non-terminal is converted to this one. After that, we have only one non-terminal, that is itself is a rightmost non-terminal as well as leftmost non-terminal. So after that, we are converting this into ID. So we can see that in this whole process, we are converting the leftmost non-terminal. And in the same second example, we are taken this one. You can see first we convert rightmost non-terminal into this one. So this approach is rightmost derivation. We will see that top-down parser try to find the leftmost derivation of the given source program. Top-down and bottom-up. I say these L in both the approach have the same meaning. That is, we are scanning the symbol from left to right. In the second, this is what? In top down, we are using leftmost derivation. This. And in bottom up, we are utilizing rightmost derivation. This is what we are telling you. LL and LR. These are other representation of these two approaches. We will see that the top-down parser try to find the leftmost derivation of the given source program. We will see that the bottom-up parsers try to find the rightmost derivation of the given source program in the reverse order. Next is parse tree. It is the representation of the derivation. So it's a graphical way through which you can easily understand how we convert a start symbol into given string. In the same manner, thus we are starting with the start symbol E, then convert it into minus E. So graphically we represent E as a left child, it will show first symbol, as a right child, it will show the second symbol. In the same manner, we can represent all the possible steps through which we are getting the required or target string. So first step, then we are converting this E into this one. So we can say this E is converted into this one. That means we are utilizing by means of this production rule. In the same manner, we have next replacement, that is this E is converted into E plus E. Then this is converted into ID, and finally this is ID. So by means of leaf, that is first symbol is what? It is the leftmost leaf. And the same manner, this is second symbol, or we can say second leaf, then third symbol means third leaf, then fourth symbol, fourth leaf, and then fifth ID, this is fifth leaf, and finally the last, that is closing brace, and this is our final leaf of the parse tree. This is how we represent the given string by means of starting symbol. Now next topic, it is also a very interesting topic, that is ambiguity. What is ambiguity? Let's talk about. A grammar produces more than one parse tree for a sentence is called an ambiguity. You know very well what is parse tree. It's a way through which we can find how this string is generated by means of which appropriate production rule. So this is first way through which we are finding our string. In the same way, I already told you strings. These are the strings, means by means of leaves we can find the string. So what is the string? First symbol is ID, then second is plus, then third is ID, then asterisk, then last is ID. So this is our string by means of first parse tree. And according to this one, let's check this first leaf, then second leaf, then third leaf, then fourth leaf, and finally is sixth leaf. Both are same, exactly same. Means if more than one parse tree is possible for a sentence, or we can say string, then this is known to be ambiguity. This process is known to be ambiguity, and the grammar is known to ambiguous grammar. So for the most parser, the grammar must be ambiguous. Every string must have a unique parse tree. If it is not, that means grammar is not a unambiguous grammar. But we need unambiguous grammar for our parser. So unique selection of parse tree for the sentence. We should eliminate the ambiguity in the grammar during the design phase of the compiler. So first we have to eliminate the ambiguity. An ambiguous grammar should be written to eliminate ambiguity. It must be, we have to prefer one of the parse tree of a sentence to disambiguate the grammar to restrict this choice. This is very well-known example. It is our CFG, that is statement first production rule, that is if expression then a statement. This is second, if expression then statement else statement. This is our second production rule. And third is statement gives other statement. And suppose it is the given string. So this given string can be obtained by means of two parse tree. So this CFG is ambiguous. Clear? We prefer the second parse tree as match with the closest. We have to disambiguate our grammar to reflect this choice. To make this ambiguous grammar into unambiguous grammar, so we need new non-terminals. First non-terminals of first productions will be statement gives match statement, and second is statement gives unmatched statement. And match statement will drive to if expression then match string else match string. And second is match statement gives other statement. And second non-terminal has two productions. First production say this unmatched statement will have if expression then statement, and second is if expression then match statement else unmatched statement. So this will clearly eliminate the ambiguity. Ambiguous grammar, because of ambiguous operator, can be this ambiguity according to the precedence and associative rules. So we can eliminate ambiguity by means of precedence and associative rules. So in this grammar we have number of operators. First operator is plus operator, or we can say additive operator. Then we have asterisk operator. Then we have power operator. and this is simple terminal. In the next we have no operator, means in first three we have three different operator and each operator have precedence set. So according to precedence, this is highest precedence, then this one, and then this one. And next, associative rule. As an associative rule, power is right to left associativity, and asterisk is left to right, plus is left to right. So convert this into unambiguous grammar, we need to convert these non-terminal, or we can say this additive operator into this way. So since it is left to right, so we need to change rightmost this non-terminal into new non-terminal. So we are using E gives T, and this E is converted into T. So E gives T, we are able to do this. And now this can be converted to next, that is T asterisk, according to this one, T asterisk T. Since it is left to right, so we need to change this one. So again we are converting this non-terminal into next non-terminal, that is F. So we need to two production rule. In the first, we will convert this T into a new non-terminal, that is F, and second, this is T gives F. So this is how we achieve unambiguity. In the same manner, now you can see this is how, this is right to left. In first two cases we have left to right, means left associative, and this is right associative. So we need to change right leftmost symbol into this way. So first convert this F into G, and this is how. Now this ambiguous grammar is completely secure for our parsers, or we can say this is an unambiguous grammar. So okay, Jain, this is all. Next topic will be discussed in next lecture. Okay, Jain to all.